Okay, so can you please confirm whether I am audible to you all now or not? Okay, thank you. And my slides are visible to you. I welcome you to the third tutorial of this course, Reagents in Organic Synthesis, which is conducted by NPTEL and whose course instructor is Professor Subhash Chandra Pant from IIT Guwahati. I'm your PMRF teaching assistant, Deepika. I'm doing my PhD in chemistry at IIT Bombay. So, in this week's course, three lectures were given to you, three video lectures, and the topics that were covered were ranging from various reducing agents, especially hydrogenation and hydride donating reagents, and also some other reducing agents like Wilkinson catalyst, Crabtree catalyst, etc. were covered. Okay, so we are going to solve together a few more questions which were not covered in the video lectures, but I would suggest please go through the video lectures very carefully, and like I suggested in the last lecture, you all can make your own notes, okay, so that it will be helpful for you, your basic understanding. Okay, so with this, let us start today's tutorial. So, this is the first question of today's tutorial where you are given this substituted pyrrole and you are given conditions which are similar to Birch reduction. Okay, in place of sodium metal, you are given lithium metal here, and at the first step, you have to carry out Birch reduction, and in the second step, you have to react this reagent with the anion that you will get in the first step. Okay, so as I have told you already, this condition is Birch reduction condition, but when you approach to solve this question, you have to know which position of this pyrrole ring will accept the first electron that will be donated by lithium metal. Okay, so for that, if you remember when you went through the video lecture, when we are carrying out Birch reduction with cyclic substrates, depending on the substituent present on the ring, whether it is electron donating or electron withdrawing, the position of the rings were accepting the incoming electron at first. And similarly, depending on the substituent present in the on the ring, you have to protonate or react with the second reagent for your nucleophilic attack. Okay, so let us solve the first question step by step. This is your substrate given, and when you react it with your Birch conditions, the first electron will come to the second position, which is containing this ester functionality. Why is it so? Because of the presence of this electron withdrawing group, this position is electron deficient. Okay, so when the incoming electron is coming to this electron rich ring, if you are placing it on this electron deficient position, it will be stable. Okay, so subsequently when you donate the electron at this position, the arrow pushing will go first, the double bond will lie here, and then this double bond will come to this position to give you an anion. Okay, so this is the first intermediate. This is the first intermediate that you are going to get. Okay, now what will happen? Protonation will take place from this base. Okay, and then your lithium metal will donate the second electron to form the new anion at the second position where you donated your electron at the very first step. So now this anion at this position is going to react with your second reagent which was given in your question. Okay, so if we go back to your question, this is the second substrate which is given. This is the second substrate which is given, and you have to react. You have, if you notice, you have a carbonyl group here. Okay, this is a carbonyl group which is attached to one chloride and one methoxy on the other side. Okay, so definitely chloride is better leaving group than methoxy. So when the anion formed at this position will attack this carbonyl, the chloride group will get eliminated and you will get this desired product as the product of your Birch reduction. Okay, so I hope the mechanism is clear to you. This has already been covered in your first lecture of week 3. Okay, so I hope you understood why the first electron was donated to this particular second position. This is because of the presence of the electron withdrawing group. So after that you were given another question, which is this. Okay, so this question also you have to solve similarly because this is also containing an electron withdrawing group, cyanide. So again you are given similar Birch reduction condition, and in the second reagent you have again an ester where you have a bromide leaving group. So you have to attack at this CH2 group so that bromide can be knocked out. So if you solve it step by step like we have done in the first question, you have to first donate your electron from lithium at this position, right? Because this is the electron withdrawing group containing position. And then the arrow will go like this, will go here, and you will get an anion at this para position of cyanide. So first that para position anion will be neutralized using proton from base and or solvent, and then when the second electron will be donated here, the anion formed at this position will react, undergo nucleophilic attack to give you your desired product. Since in your question, if you see, this is the electrophilic agent given here. So your anion will react at this CH2 and bromide will be knocked out. So among all these three types of products, you will get this particular product for this reaction. Okay, and these products you will get depending on the electrophilic reagent that is being given to you. Okay, so need not to worry about these two for now. This is the product that you are going to get for this question number one reaction. So I hope this is clear to you. This question is from Birch condition. Okay. So let us move to the next question now. This is the question number two. You are given a diene here. Okay. You have a cyclopentane ring and it is containing two alkyl chains which are having two dienes. And if you look at the reagent given, you are given a catalyst which is rhodium catalyst along with gaseous hydrogen in benzene solvent. So if you remember this structure, you might have already figured out that this is the Wilkinson catalyst. Okay, and Wilkinson catalyst topic has been covered, and you have to remember that whenever it comes to hydrogenation of olefins, Wilkinson catalyst always gives you syn addition of hydrogen. So one more thing, different types of olefin react with different rates with Wilkinson catalyst. Okay, like for example, if you see, these are different types of olefins: monosubstituted, disubstituted, disubstituted syn, trans, trisubstituted, and tetrasubstituted olefins. So this is the rate of binding, relative rates of binding affinities of different olefins to the Wilkinson catalyst. Okay, so if you see here, when we are treating this diene with our Wilkinson catalyst, one equivalent, only one olefin is getting reduced, and you are getting a saturated hydrocarbon on this side. So why is it so? Because if you look at the geometry of the two double bonds, one is cis double bond, that is having Z stereochemistry, and the other is E olefin. Okay, so looking at this relative binding affinities of different olefins, you have already known that cis double bonds are more readily reduced than trans, and this is because of the steric interactions between the catalyst and the substitutions on the olefin. Okay, so this is why when we are taking only one equivalent of the Wilkinson catalyst, the cis double bond will be more readily reduced. Okay, I hope this is one easy question. Let us move to some more questions. Yeah, so this is again Another question from the same topic, which is Wilkinson catalyst. So again, you have two double bonds present here in the two rings. One having adjacent to the cyanide group. This is the left side double bond, and one is this right side double bond. Okay. So if we reduce it with Wilkinson catalyst, can you guess which double bond will be preferably reduced?
Left side double bond.
Yes, very good. So if we are taking only one equivalent of the Wilkinson catalyst and you have these two double bonds, the left side double bond will be preferentially reduced. Very good. So why is it so? The reason is, if you have more than one unsaturation and one of it is containing a polar functionality, then that particular unsaturation will be reduced first. Okay, because these polar substituents present at the adjacent position helps this the unsaturated bond to bind to the catalyst more easily. Okay, here it is written, unsaturated substrates containing polar functionality are hydrogenated more rapidly. It may be due to easy coordination of olefin to the catalyst that is assisted by polar functional group. So, since we have a polar substituent on the left side ring, this is why the left side double bond is more readily reduced. So, I hope you have noted this down, because this particular point was not extensively discussed in the video lecture, so you can note it down. Okay, again, this is one more question from the same topic, which is Wilkinson catalyst, and here you have this bridged compound, and you have a double bond which is exo. Okay, and you have to reduce it with Wilkinson catalyst, one equivalent. So basically, in this particular example, you have to guess the stereochemistry. Okay, because after reduction, this double bond will get converted into methyl, and you have to guess correctly in the major product, the newly forming methyl will go to the equatorial or axial. Okay, so let us look at the steric factors which will play a major role in the formation of the major product. Okay, so let us see how these two kind of products are forming and how one of these will be the major one. When you treat this exo double bond with Wilkinson catalyst, the catalyst can bind to the olefin from above and below. Okay, but you have to remember that the binding of the catalyst will prefer that particular phase which will have the least steric hindrance. So if you look at the substrate, the below side phase, if you see, it is containing one ethyl group along with 4 carbons of the substrate. Okay, 4 carbons and the ethyl group. So this below face is definitely facing a lot of steric hindrance. Whereas the above face, if you look at, only one carbon of the bridge is lying on the above face, or you can say exophase. Okay, so this is why the catalyst will preferably bind to the double bond from the exophase, which is above face. So definitely, whichever phase the Wilkinson catalyst is binding, from that same phase it is going to donate its hydride, right? So hydride donation will preferentially take place from the exophase, the above phase, and you will get this endo product as major, because when the hydride is coming to this position, this newly formed methyl will get automatically pushed back, and this methyl will lie at the equatorial position. So out of these two endo and exo products, you will get this endo product as the major one. I hope this stereoselectivity in this Wilkinson catalyst reduction is clear to you all. Okay, always remember the steric factors play a major role in Wilkinson catalyst and as well as Crabtree catalyst. Okay, so while reducing bicyclic substrates like these, you have to choose the phase which is experiencing least steric hindrance, and from that phase only you have to transfer the hydride, and the double bond which will get converted into a saturated hydrocarbon will get pushed back. Thus, this product will be your major product for this particular question. So, let us move to the next question now. So, this is another question from the topic reduction. Okay, two types of reagents are given here. One is palladium supported on carbon and hydrogen, and the second one, if you look at the structure, it is your Crabtree catalyst, okay, which is a iridium catalyst, and you are given this particular alcohol, and you have to treat with two different reducing agents. One is palladium supported on carbon, and the other is Crabtree catalyst in presence of hydrogen in dichloromethane solvent. So you have to guess what kind of products will you get in presence of these two reducing agents. Definitely you will get two different types of products, and which product will you get for which reagent, that you have to guess correctly. Okay, so if we look at the product ratios formed, see, after reduction you can get these two types of products, right? Because when your hydride will come from the above or below phase, your this methyl will either get pushed back or it will go towards us. Okay, so it will be either syn to the alcohol or anti to the alcohol. If you look at the product ratios, when you are using palladium carbon, product 8 is a minor product and product 9 is a major product. But When we are using Crabtree catalyst, you are almost exclusively getting product 8 as the major product. So since this question is from the topic Crabtree's catalyst, you have to tell why we are observing this opposite selectivity in case of Crabtree's catalyst. The reason you can find from this proposed intermediate. You don't have to go deeper. You just have to look at the alcohol functionality. Okay, what happens is you have a metal surface in the Crabtree catalyst, right, which is iridium. So when you have such polar groups containing lone pair electrons, they can bind to the or coordinate to the metal surface and can, can facilitate the hydride donation from the same phase as the polar group. Okay, like here, if you look at the substrate, you have an alcoholic functionality, right? So this alcohol will bind to the iridium metal surface, and because of this binding, the hydride will be donated from the same side as the alcohol. That means the binding face of your Crabtree catalyst will be towards you, right? So if you are donating your hydride from the face which is towards you, this methyl will get pushed back. Okay, this is why in case of iridium catalyst, you will get this product as major. But in case of the palladium supported on carbon catalyst, the selectivity will be reversed because polar groups can poison the catalyst surface. Okay, so whenever you have hydrogen on palladium carbon, you have to transfer the hydride from the face which is opposite to the polar groups, because polar groups can poison the catalyst surface. Okay, so this is why this kind of selectivity is observed in case of palladium carbon and Crabtree catalyst. So I hope you understood selectivity, which is coming from the uh, binding affinities of the substrates. Okay, let us move to the next question. Again, another question is coming from the Crabtree catalyst topic. You are given this tricyclic substrate, okay, and you have alcohol, ester, and ether functionality along with this tetra substituted olefin. So you have to subject this substrate 20 with Crabtree catalyst. Of course, you are going to reduce this double bond, but while writing the structure of the product, you have to specify that this methyl group will be syn to the alcohol or anti to the alcohol. Okay, so the reactivity will be similar to the last question that we have solved. So, like we saw, this alcohol is going to bind to the iridium metal surface, right? After the binding, the incoming hydride, which you are going to transfer to the double bond, will come from the same phase as the alcohol. And in turn, your alkyl group will be pushed back to the opposite phase. This is why on the product side, if you see, you have the alkyl group, methyl group, and your hydroxy group anti to each other. Okay, so this is definitely coming from the transition state that we saw in the last question. If you remember, this kind of transition state, if you see, is getting formed in presence of hydroxy functionality, and from the same phase the hydride will be donated. This is why your methyl and hydroxy will be trans to each other. So after you know these selection rules, that what are the factors you have to remember, whether it is coming from steric reasons or whether it is coming from coordination with the metal's surface, you will no longer find these questions difficult. Okay, so
हाँ बोलता रियलमी 11 5G ना सब स्मॉल में
okay, I would request you all to please mute your microphones so that
मैं अथी कौन WPA2 होगी सेक्योर तो वैसे पासवर्ड कथी कलर इधर A33 444
Small double T.
okay, can you please mute your microphones? Okay, so next question is coming from the LH reduction part. Okay, there are so many questions that were solved in the video lectures, which were from LH, NaBH4, lithium borohydride, uh, sodium cyanoborohydride, etc. So let us solve this question step by step. You are given this cyclohexanone having a tertiary butyl substituent, okay, and you are treating it with one equivalent of lithium aluminum hydride and of course the workup. Okay, so if you reduce this substrate, definitely the reduction is going to take place on this ketone, and as a result of the reduction you are going to get alcohol. Okay, hydroxy functionality is going to form as your product. Now you have to specify the newly formed hydroxy group will be axial or equatorial. Okay, so for that you have to look at two factors: the formed in the formed product, which product will be more stable, whether it will be the axial hydroxy containing or equatorial hydroxy containing. You have to look at that stability. Okay, so if you carry out the reduction, you will see that this particular product you will get as your major product, where you have the hydroxy group in the equatorial position. Why is it so? The plausible explanation for this behavior is the hydroxy group prefers the equatorial position to avoid the interactions with other axial hydrogens. Definitely, this explanation is coming from the 1,3 diaxial interaction of common cyclohexane structure. Okay, so if you place your hydroxy group in the axial position, this is going to experience 1,3 diaxial interaction with your axial hydrogens. Okay, so in this particular question The major product will come from the stability of the product that is being formed. So the product which is containing the equatorial hydroxy group will be more stable, and you will get this particular product as your major product. But one thing you have to remember, one thing you have to remember that if you had this tertiary butyl in the axial position, suppose at this position, in that particular question, you have to see the steric hindrance of the approach also. But for this particular question, you only have to see the stability of the newly formed product. So another question is coming from LH, which is a very easy question. You are given an epoxide here. This is propylene oxide, and you have to treat it with one equivalent of lithium aluminum hydride followed by the hydrolysis step. So you have two positions of the epoxide from which the incoming hydride can attack and open up the epoxide ring. Okay. So you have to choose which carbon will it choose. Okay. So when it comes to hydride donation, you have to always remember the less sterically hindered position is attacked first. So this one you can see is substituted with one methyl group, whereas this carbon is not substituted with any other alkyl chains apart from the epoxide ring. Okay, so if we talk about the steric hindrance, this carbon is the least sterically hindered one. So the approach will come at this carbon first, and you will get opening of the epoxide ring from this side. Okay, and this is the product that you are going to get. After the opening of the epoxide ring, the newly formed alcohol functionality will be contained by the more sterically hindered carbon, because we are opening the ring from this side. Okay, so always remember that hydride donation will take place from the least sterically hindered side of an epoxide. So after this, let us move to the next question. So this is another question from the LH reduction part, lithium aluminum hydride reduction. Reduction of 1 methyl pyrrolidine to one with 2 equivalents of lithium aluminum hydride will give. See, they are specifying 2 equivalents of lithium aluminum hydride. And this is the substrate that is given, 1 methyl pyrrolidine 2-one. Okay, and these are the 4 possible products that you can get from the LH reduction of this substrate. But to know exactly which product is going to form, you have to solve this question step by step. Okay, see, this general substrate which is similar to your substrate given, you have to just uh, focus on the carbonyl group. Okay, hydride will be donated to the carbonyl group, and you will get this kind of an intermediate oxyanion. Then the lone pair of electron from the nitrogen will be pushed towards the carbonyl carbon, and your oxygen will be completely knocked out from your substrate, and in turn you will get an iminium ion. Okay, now this positively charged iminium ion will be reduced by the second equivalent of lithium aluminum hydride. Okay, remember you are given two equivalents of lithium aluminum hydride. So second equivalent of your lithium aluminum hydride will neutralize your positively charged iminium ion. Okay, and you will get this tertiary amine. Okay, so if you look at the options given, which product you will get by reducing this substrate with two equivalents of lithium aluminum hydride, your answer should be option A, 1-methyl pyrrolidine. Okay, no to all, no to all, no to all, because your oxygen functionality, your carbonyl functionality is completely removed, and the product is simply a tertiary amine. Okay, so 1-methyl pyrrolidine you are going to get as your major product. So do not get confused. Do not stop at the So I was saying, do not stop at the alcohol step. Okay, sometimes you forget that you are given two equivalents, so you might hydrolyze this particular intermediate product and report the product to be maybe 1-methyl pyrrolidine 2-ol, but you cannot forget the second equivalent of your lithium aluminum hydride. Okay, so you have to reduce your iminium ion with the second equivalent, and you will get the tertiary amine as your final product. So after this, let us move to this question. Here you have a cyclohexenone with an alkyl chain containing a carboxylic acid group, and you are treating it with sodium chloride, sodium borohydride in methanol. And this reaction condition, if you remember, is nothing but Luche reduction condition. Okay, Luche reduction condition. So you have to remember this particular condition you have studied to be more selective towards ketone. Okay, and when you have possibility of 1,2 addition and 1,4 addition in alpha beta unsaturated ketones, they will always prefer 1,2 addition of the ketone. That means they will not touch the alpha beta unsaturation, they will only react with the keto group. Okay, that is the specialty of Luche reduction. So what will be the product that you are going to get here? Because you have one carboxylic functionality, carboxylic acid functionality here, which can react with the ketone or its reduced product also. Okay, so if you look at the reactivity of this substrate, you have to see that at first, as expected, your keto group will be reduced. Okay, your keto group will be reduced and you will get an alcohol at this position. Now in the second step you are given 9 equivalents of hydrochloric acid. Okay, strong acidic conditions are given to you. So in presence of acid, what happens? The alcohol that will be generated after Luche reduction will be protonated and your water will be removed and you will get a carbocation like this. I hope this first step is clear. What happens in the first step? Your keto group is being reduced by your sodium borohydride in presence of sodium chloride, and that alcohol which is forming by the result of reduction will be protonated by your acid and it will be eliminated as water and you will get this carbocation. Now you have a possibility of forming a 5-member ring using this alcohol which is in a very near periphery. So this acid this double bond reacts with this double bond and this double bond will shift to the carbocation to neutralize it. As a result, you will get a product which is a spirocyclic lactone. Okay, the final product that we are getting is a spirocyclic lactone. This is getting generated because this acid is attacking at this carbon and your double bond will move here and this carbocation is getting neutralized. So this lactone product you will get as a result of this Lewis reduction followed by acid conditions. So if you did not have this acidic condition present in the second step, you could have stopped at the Lewis reduction product only. Okay, but since you are getting a strong acidic condition here, you have to react it further. You have to form this carbocation and you have to react this carbocation with the carboxylic acid functionality. So again, you have another question from the lithium borohydride topic. Okay, you have amide functionality here, ether functionality here and ester functionality here. Okay, and we are treating it with lithium borohydride in THF. You have to guess which particular functionality will preferentially react with your lithium borohydride. You have to always remember, whenever you have lithium borohydride, they selectively reduce the ester functionalities. Okay, they do not react with amides, aldehydes, ketones, or even acids, but esters are preferentially reduced by lithium borohydride. So whenever your substrate has many functionalities and you are given only one equivalent of lithium borohydride, you have to always go for your ester functionality. Okay, so this will be your final product where you are getting the reduction of your ester functionality. Now another question where you have a ketone which is containing an alkoxy substituent at the alpha position and we have to treat it with aluminium isopropoxide in presence of isopropanol in toluene solvent at 50 degrees Celsius. And if you look at the product, you are getting a product where your hydroxy and alkoxy, these two substituents are syn to each other. So you have to rationalize why you are getting this syn product as your major product. Why not NT? Because if you look at the product, if you look at the substrate, your carbonyl is planar, right? and you can add your incoming hydride from above or below the phase. But this alkoxy substituent is directing the hydride to come from either above or below the phase preferentially. So let us look at the mechanism of this reaction. Then you will understand how you are getting the syn product preferentially. So this comes from the Felkin model. Okay, the if you do not have much knowledge about Felkin or Felkin-Ahn model of nucleophilic addition, you can go through video lectures of the course Introductory Organic Chemistry. Okay, in that course, this particular topic has been extensively covered, or now also we can revise it quickly. So what happens, this is your substrate, okay, which is containing a, suppose, methoxy substituent you have at the alpha position, and in the question you are given this condition, okay, which is Mirwin Pondorf Verley reduction condition. So according to Felkin-Ahn model, you have to place your carbonyl at the top face like this, okay. Linearly, you have to place your carbonyl as shown here. Then to the second carbon of this junction, like I'm talking about this carbon now, this carbon we are going to place at the back side, okay. And while placing this carbon at the back side, you have to place the largest group attached to this carbon perpendicular to your carbonyl group, okay, because this particular conformation where your largest group is perpendicular to your carbonyl group is the most stable conformation of your substrate, okay. So after placing the largest substituent perpendicular, now you can place your phenyl and hydrogen according to your clockwise or anti-clockwise direction, okay. And definitely they will be lying in this fashion, okay, with a gap of 120 degrees. So the placement is done. Now you have to react your substrate with the incoming hydride. So how will you react it with your hydride? Like in which direction the hydride will come? The hydride will come from the side of the smallest substituent present on your alpha carbon. So you have phenyl, methoxy and hydrogen present at this carbon, right? And hydrogen is the smallest group present at this carbon. So the incoming hydride will attack from this side of your substrate, and in turn your this hydroxy will be pushed this side, okay. I will show by maybe drawing, okay, so that you can clearly understand. See what happens. This is your this is your smallest substituent present at the alpha carbon. So your hydride is coming from this side, and in turn your carbonyl oxygen will get converted into hydroxy, right? Because when the hydride is coming here, your arrow will go to this carbonyl oxygen, and this group will be pushed till here as a hydroxy. So after the placement of your incoming hydride and hydroxy, and of course the phenyl present will also shift here because of the hydride attack. You can revise your Falcon-Ahn model if you are finding this explanation a little difficult. So your hydroxy and phenyl will be pushed like this, and after you get the product conformation, you will see that syn product is preferentially forming as your major product. Okay, so thus in this particular reaction where you have to carry out Marvin-Ponder-Warley reduction of your ketone, you will always see the methoxy and the newly formed hydroxy will lie syn to each other. And the explanation is coming from the Falcon-Ahn model. So now let us move to the question number 12, where you have an aldehyde and you have to treat it with sodium cyanoborohydride in presence of ammonium acetate with aqueous ammonia and ethanol solvent for 18 hours. Okay, and the product that you are getting is a primary amine. So what happens, this reaction condition is extensively used for the synthesis of primary amines. Okay, and this condition is involving reduction using sodium cyanoborohydride. Let us look at the reaction mechanism so that you can understand how you can get the product to be a primary amine. So the ketone reacts with your amine present in the reaction condition. If you go back to your reaction condition, here you are given ammonia and ammonium acetate. Okay, so you just have to react your ketone with ammonia and you will get an imine like this. So if you have ammonia, this R2 also will be H in your case. Okay, and now this imine will be reduced with sodium cyanoborohydride and you will get an amine as the compound 4, where you will have a hydrogen at this position because your R1 and R2 your R2 on the amine is H because you are taking ammonia in your reaction condition. Okay, so this is your product which is amine. At this stage only you have to stop because your reaction conditions are simple. You are only treating your your aldehyde with ammonia and reducing it with sodium cyanoborohydride. So this amine is going to be your product. You don't have to go further because uh, if you are given two equivalents of the amine and two equivalents of the sodium cyanoborohydride, then only you have to proceed. But in the condition no use of excess reagent is mentioned, so you only have to treat it with one equivalent of ammonia and one equivalent of sodium cyanoborohydride, and this will be your desired product. So I hope this sodium cyanoborohydride reaction was clear to you, and like I said, this particular reaction is extensively used in industry for the synthesis of primary amines from aldehydes. Okay, and similarly secondary amines can also be generated depending on the substrate and also depending on the base. So with this we have arrived at the end of this question answer session. So we have solved 12 questions from the topic covered in the week 3 lecture, which were from the various topics of reduction reactions. Okay, let us just quickly go through the questions again so that you can revise and you can remember how you have to approach while solving these questions. Okay, so at first we started the question series with these two burst reduction questions, and you saw that both the substrates were having electron withdrawing groups on it. Okay, so the first electron that was coming from the metal was preferably attacking at the position which is containing the electron withdrawing group. Hence, we were getting these two products involving this kind of reaction mechanism. And in the second step, we saw that the second carbon ion that was forming was reacting with electrophilic reagents to give you alkylation at the second carbon ion. So after this, we went to solving these questions from Wilkinson catalyst, and we saw how syn olefins are readily reduced over anti-olefins, E-olefins, because of steric reasons and relative binding affinities. Okay, and when you had two olefins and one of which was containing a polar group adjacent to it, we preferentially reduced the polar group containing double bond, because we studied that this is because of the easy coordination of olefin to the catalyst in presence of a polar functional group. Then this highly steric substrate was treated with Wilkinson catalyst, and two types of products we were getting. One was endo product and one was exo product. And we saw that the product where the catalyst was binding from the less sterically hindered phase was the major product which was forming in the reaction. Then we moved to the treatment of this substrate with palladium carbon condition and with Crabtree catalyst, and we saw that selectivity of the yields were different, because in case of Crabtree catalyst, the alcohol functionality was binding to the metal surface. This is why the incoming hydride was always coming from the phase which is syn to the hydroxy. And this is also the similar question. Here also we saw assistance of this alcoholic functionality, due to which the hydride was coming from the same face of the hydroxy and the methyl was being pushed to the opposite face. Then we saw this lithium aluminum hydride reduction question, where we saw that the newly formed product's stability was dictating which will be your major product, axial hydroxy or equatorial hydroxy. And we saw that hydroxy, which will be in the equatorial, is giving you the more stable product. This is why you will get this product as the major product. Again, we studied LH reduction of oxiranes or epoxide, and we saw that hydride was coming from the side where you have no substitution on the carbon, because the least sterically hindered site is preferred for the hydride addition. And we were getting this alcohol as your major product. Again, we solved this question where we treated 1-methyl pyrrolidine 2-one with 2 equivalents of lithium aluminum hydride. Okay, and you have to remember here we are using 2 equivalents of lithium aluminum hydride. So you cannot stop at this hydroxy functionality product. Okay, you have to react it further to get this iminium ion, which will be reacting with the second lithium aluminum hydride, and it will give you this tertiary amine as your major product, and option A we were getting as the major product. And then this Leuch reduction question we came across, where we reacted this cyclohexenone with Leuch reduction condition to get an alcohol here, and because of the presence of strong acidic condition, we had to eliminate that hydroxy group, right? And we got this carbocation. Now this carbocation reacted with the intramolecular carboxylic group to give this spirocyclic lactone. Then we talked how lithium borohydride always preferentially reacts with ester functionality over all other carbonyl groups. Okay, and it will always go for the ester functionality first. And then we talked about the stereochemistry of this Marvin-Pondov-Varley reduction, and I have also suggested all of you to go through the Falkin-Ahn model revision, because that will help you understanding how we are getting this seen product in case of this Marvin-Pondov-Varley reduction conditions. Okay, and then lastly we talked about this industrial synthesis of primary amines from aldehydes, where we were treating our aldehyde with ammonia to get an imine, and that imine was selectively reduced using sodium cyanoborohydride, because sodium cyanoborohydrides are used for selective reduction of imines, carbon double bond nitrogens. Okay, so thus we have solved all these questions. I hope these were clear to you. Please feel free to interact regarding any queries or doubts if you have regarding this week's lectures or this week's questions which have been discussed. And I would suggest you please solve the assignment questions as well, because they are also very helpful in understanding the concepts. Okay, so thus we have come to an end of today's session. Okay, thank you so much everyone for joining.
Thank you, madam.
Okay,
Now, Deepika, I have one doubt. Hello,
yes, yes,
can you hear me?
yes, yes.
In this week assessment, there was one question where there is quinoline structure was there. In
Okay,
that they were that the quinoline they are putting the bridge reduction, and then they are adding the RMGX.
yes,
Only RX can react, but RMGX how it will react with that quinoline compound? So we'll get 1,4-quinoline after the bridge reduction. But
yes,
after
yes.
that, how this RMGX will react?
Yes, yes. You need electrophilic reagent, right? For
Yeah.
reacting with the anion, the second anion which is forming.
Yeah.
Okay, so
But but it will not react with RMGX, no, because the R will be in a delta minus position.
yes,
It's a
yes,
delta minus.
yes, yes.
Yeah.
You already have an anion on the substrate, and then if you are treating it with RMGX, you have R minus only.
Yeah.
So there could be a mistake in the question. I will go through the question again. Okay.
Okay, ma'am. That's what I was. I was what to say, breaking my head to solve that question. But how this anion will react with the RMGX? It never react with the RMGX.
Yes.
So please
Maybe
go through, ma'am. Go through on
maybe
that.
it can be Rx, or there can be some mistake in the question. Okay, do not worry, your concept is correct. Okay.
So I got less points to that. How it will be corrected.
Okay, okay. I will just check the question and confirm how they have placed the question, because I at this point I do not really remember the substrate. I will just go through the question again and I will confirm in the next session. Is that okay?
Can I show? Can I share now? Is my desktop
Yes, yes, sure.
just? Can you see my screen?
Yes, yes, I can see.
See, this is the question.
Okay, yes. There has to be some mistake because it cannot be methyl magnesium bromide.
Okay. Okay, Deepika. Okay, please
Yes,
go through it and then
yes.
please let us.
I will just confirm once again
Hmm. Yeah.
whether there is any mistake or not, because according to the basic concept you need an electrophilic reagent in the second step to react with your anion, right? So
Yeah. Yeah. Yeah.
yeah, I will
Hmm.
confirm you in the next session. Thank you so much for expressing your query. Okay.
Thank you. Thank you. Thank you,
Yes,
Deepika. Thank you.
yes.
Bye.
Okay, thank you so much.
Thank you. Bye.
Okay.